Well, first of all, let me thank Kathy for inviting me to give this talk. I would say that, except for that, she has done a very good job in organizing this session. So most of what I'm going to say is about a joint work with Bruno Mendonça from São Carlos, with the same title as the one of this talk. Well, you all know what an umbilical submanifold is. This slide is just an excuse to introduce some notation. So, an isometric immersion is umbilical if the second fundamental form has this simple structure here. Roughly speaking, a submanifold is umbilical if it's equally curved in all tangent directions. Umbilical submanifolds are the simplest possible submanifolds besides totally geodesical ones, at least as far as the structure of the second fundamental form is concerned. The classification of umbilical submanifolds in space forms is quite well known, and recently there has been some interest in studying umbilical submanifolds of more general remaining manifolds. In fact, I was first interested in looking for umbilical submanifolds in Sn cross R after attending a talk by Tubiana a few years ago, in which he reported on the results of this joint paper with Rabaswan. In this paper, they have been able to classify umbilical surfaces in all of Thurston geometries, as well as the Berger spheres. But in fact, most of their results are non-existence theorems. The only of Thurston geometries that admit umbilical surfaces are the Sol group and the product spaces S2 cross R and A2 cross R, besides space forms, of course. And the richest case are those of the product spaces, for a reason that will become clear in a while. In this other paper, the authors gave a local description of umbilical hypersurfaces of Sn cross R of any dimension. So our initial goal was to extend the results to submanifolds of arbitrary codimension. And this is in fact part of a bigger program of trying to classify umbilical submanifolds in an arbitrary product of space forms. And one good reason for trying to do that is this nice theorem by Yuri Nikolaevsky, which states that a totally umbilical submanifold of dimension at least 3 of a globally symmetric space is actually a totally umbilical submanifold of a product of space forms which is totally geodesically embedded in the symmetric space. So, by classifying umbilical submanifolds in products of space forms, one is actually classifying such submanifolds in an arbitrary symmetric space, at least in dimension greater than 2. Well, I should say that we are not too far now from achieving that goal, except for the case of surfaces and conformally flat products of space forms. I mean, a product of space forms whose factors have curvatures of equal absolute value, but different signs. Well, a basic fact related to our problem is the existence of this conformal diffeomorphism between, say, Sm plus 1 cross R and Euclidean space with the origin removed. It's given explicitly by this formula. So this product space is conformally flat And this makes us think that our problem is already solved even before we just start to think about it. Because it's well known that a conformal diffeomorphism preserves umbilical submanifolds. So umbilical submanifolds of this product space are just images of round spheres or a fine subspace by the inverse of this map. However, some interesting questions remain to be answered. For instance, when are two of those submanifolds congruent by an isometry of this product space? In other words, what are the congruence classes of umbilical submanifolds in such product spaces? On the other hand, what's the geometry of such a submanifold like as a submanifold of this product space? So in order to state our result, well, today is Friday, the last day of the conference. You may be tired, and I'd rather draw a picture so you don't have to read that and think of the picture by yourselves. So let us look at Euclidean space of dimension m plus 2 as a product in which this plane represents Euclidean space of dimension m plus 1. And here we choose a point, x bar, and from it we raise a half line parallel to the factor r. And at each height h, we consider this hyperplane orthogonal to this line. And inside it we take this sphere centered on this line. This is what I'm denoting by SMRH. And then we just take its image by the inverse of that map. So as we vary R and H, we get a two-parameter family of submanifolds of Sm plus 1 cross R. All of them, of course, diffeomorphic to the sphere, except for a single element, which the one we get at height 0, passing through the origin. And my claim is that such maps are the representative of all congruence classes of umbilical submanifolds in Sm plus 1 cross R. So, part of these statements are obvious. They just follow from the fact that a conformal diffeomorphism preserves umbilical submanifolds. This is just due to the fact that totally geodesic hypersurfaces of this product space are just the images by this map, the inverse of phi, of hyperplanes through the origin in Euclidean space. So this part of the statement explains what is the geometry of such a submanifold like as a submanifold of the product space. It's a rotational submanifold in a precise sense that I will give later. And the profile curve is a curve in a totally geodesic submanifold S2 cross R, or could be S1 cross R if it's the image of a sphere whose center is at x bar. So they all have codimension, substantial codimension 2, which means they lie in a totally geodesic submanifold of the ambient space in codimension 2, except for one parameter family which has substantial codimension 1. And these are the ones that have been studied previously, although not with that description. So I think the most interesting part is this one, which just says what I have just told you. This two-parameter family gives you representatives of all congruence classes of submanifolds in those product spaces. And we also have been able to obtain an explicit parameterization of all such submanifolds as a rotational submanifold in the ambient space. And for that, it's more convenient to use these two different parameters, P and Q, instead of R and H, which are related to P and Q by this diffeomorphism. So for each pair of points in this subset, bounded by two parabolas, we define this open interval and this real function. And here is the explicit parameterization of any such submanifold. And in this parameterization, it already becomes clear that it's a rotational submanifold. This curve with these four coordinate functions is the profile curve. It lies in a totally geodesic S2 cross R inside the ambient space. So the parameterization is explicit. It all involves this function age. But actually, this parameterization only covers part of the submanifold. I mean, the image of a region that greater than a half sphere, but it does not cover all of the sphere. So to cover the other part, we have to use this other map, which is just congruent to the former one. So both together cover the whole submanifold. So we have an explicit parameterization of all such submanifolds. Well, a brief outline of the proof. We first show that an umbilical submanifold is always rotational, or it's an umbilical submanifold always lies. Well, I forgot to say, besides that two-parameter family, we have obviously a further one-parameter family, which are small spheres in a slice. Then we have to prove that umbilical submanifolds lie in those product spaces with substantial codimension true. This means that they lie in a totally geodesic submanifold of those spaces in codimension true. And knowing those two facts and using the umbilicity condition, we are able to get a system of ODEs for the coordinate functions of the profile curve. And fortunately, it can be solved explicitly. And this gives rise to that parameterization YPQ I showed you before. And then we just have to check that the image of such a map parameterizes this two-parameter family of spheres with R and H related to P and Q by that diffeomorphism I showed you before. Well, in order to prove the first part, we have actually to deal with a much more general class of submanifolds, which I will try to convince you that are worth looking at. But before that, let me remind you of the fundamental equations of a submanifold in a product space. So, most of what I'm going to say now applies for both Sn cross R, Hn cross R, and even Euclidean space if we take this factor as n-dimensional Euclidean space. So this symbol will denote either of such models of the space forms. And then a basic fact is that this unit tangent vector field to the factor r is a parallel vector field, of course, and if you decompose it in tangent and normal components and differentiate this equation, and you take the tangent and normal components, you get those two basic equations relating the derivative of the vector field T and the second fundamental form, the same for the normal derivative of eta. And the Gauss-Kodály-Rich equations can be written down in this way. The Rich equation is just the same as that of a submanifold in the space forms. In the Gauss and Kodály equation, there appear those two vector fields, T and eta. And in the case of hypersurfaces, it was shown by Benoit Daniel that those equations completely determine a hypersurface in a product space up to isometries of the ambient space. And recently, in a joint work with Jorge Lira and Feliciano Vittorio, we have been able to extend this result for the case of arbitrary codimension. Well, if you're not willing to do so, you don't need to read that. You can be satisfied with this shorter statement. Those equations completely determine the submanifold of up to an isometry of the ambient space. This is the existence part. If you start with those data, you can produce a submanifold in that product space, and this is the uniqueness part. Two submanifolds which have the same data differ by an isometry of the ambient space. This is in fact a particular case of a more general result that applies to an arbitrary product of space forms. Excuse me. So here's the class of a more general class of submanifolds that I have mentioned before. In the lack of a better name, I have named them class A. What's class A? It's a class of submanifolds that have the property that the vector field T that I defined before, recall this is just the tangent component of the unit vector field spanning this factor R. So this vector field T has to be an eigenvector of all shape operators of the submanifold. Let me show you how to construct such submanifolds. So we start with a submanifold of the base space, which admits an orthonormal set of parallel normal vector fields. In particular, you can take G as a submanifold with flat normal bundle. And in fact, that property is not too far from this other one. Then, of course, the vector subbundle is spanned by those vector fields is parallel and flat. And this is just a few more notation. I have to introduce these canonical inclusions. And I will denote En plus 2, either the Euclidean space in case epsilon is 1. Recall epsilon is the curvature of the base space. Or Lorentzian space in case epsilon is minus 1. So now, I just look at the submanifold as a submanifold of the Euclidean ambient space and look those normal vector fields as normal vector fields along this new submanifold and just add this unit vector field spanning the factor R. So of course we still get parallel and flat vector subbundle of the normal bundle of this new submanifold. And so we can define this vector bundle isometry between this trivial bundle and the vector subbundle Ruy tilde in this way. And with all that, we can now define a map from the product of n with an open interval, which, regarded as a submanifold of the ambient Euclidean space, is given in this way. This may seem complicated, but we are doing something very simple. We are just taking this curve alpha in the cylinder sitting inside a fiber of the vector subbundle Ruy tilde, and then parallel transporting it with respect to the normal connection of the submanifold. This is how you generate this submanifold. And this expression is simple enough to enable you to make all computations you need, and it turns out that this is a submanifold in class A. What's more interesting is that in this way you actually get all of them. So this submanifold is actually a particular case of general construction that has been introduced by Carter and West, which is called a partial tube. So a partial tube is a submanifold that you generate in this way. You start, you start with a given submanifold, take another submanifold in a normal space of that Formula 1, and then parallel transport it along the normal, with respect to the normal connection. Of course, for this to work, the submanifold has to be invariant by the normal holonomy group. And at the time I started to think about this problem, I was working in another paper with Claudio on this notion of partial tubes. So by some time, I used to see partial tubes in everywhere. I just looked through the window and used to see a partial tube flying out there. So this is how I realized submanifolds in class A are partial tubes. Okay, a special case of submanifolds in class A are those with flat normal bundle. In this case, it turns out that being in class A with this additional property is equivalent to the submanifold having flat normal bundle regarded as a submanifold in the flat ambient space. And such submanifolds are generated by starting with a submanifold with flat normal bundle in the base space, in terms of the construction I've just shown you. So class A is particularly interesting in two special cases. First, in the case of surfaces, in which being in class A already implies flatness of the normal bundle. So any surface in class A is actually a surface in this product space that has flat normal bundle when regarded as a surface in the flat Euclidean space. And also the same holds for the case of hypersurfaces. This condition, of course, is automatic in the hypersurface case. So any hypersurface in class A is a hypersurface which, regarded as a submanifold in codimension 2 of the flat ambient space, has flat normal bundle. So, in the case of hypersurfaces, submanifolds of class A have an alternative description which turn out to be more convenient for certain applications, which can be roughly described as follows. You start with any hypersurface in the base space, and then take the family of its parallel hypersurfaces, which can be parameterized explicitly in this way. So here, C and S are those standard functions. So GS is just the hypersurface you obtain by walking a distance S through each point of G along the geodesic normal to it. Then you can define a submanifold of the product space in this explicit way. You just take this point in the base space and raise a distance along the factor r, which is given by an arbitrary function of the variable I, s in I. It turns out that this description is equivalent to the one I just gave you. So, it's the same statement. In fact, this is done in a previous work by myself. And just to show you an application, well, maybe I just come back here. You can use this to generate interesting examples of constant mean curvature hypersurfaces in the product space. For that, you just have to start with an isoparametric hypersurface of the base space. Of course, this is more interesting in the spherical case, in which isoparametric hypersurfaces are very rich. So you start with an isoparametric hypersurface in the base space, take the family of its parallel hypersurfaces, which are also isoparametric, and then you have to choose a particular function A, which is completely determined in terms of the mean curvature vector function of the isoparametric foliation. Now, this is just what you have to read in this statement. It's too long. So the function A you can compute in terms of phi, which in turn is given in terms of psi, which is given in terms of the mean curvature function of the isoparametric foliation. So in this way you get a hypersurface with constant mean curvature h, this number here, which is in class A. And in this way you get all such constant mean curvature hypersurfaces in class A. Of course, if you do that either in Euclidean space or in hyperbolic space, you only have as isoparametric hypersurfaces, well, in the case of Euclidean space, products of round spheres with Euclidean factors. So this only gives you rotational hypersurfaces, the usual rotational hypersurfaces with constant mean curvature. But in the case of the sphere, it gives you some interesting families of constant mean curvature hypersurfaces. Well, let me skip this other application and just mention, Fernando is there, that another relevant class of hypersurfaces in class A are those with constant sectional curvature, which have been completely classified in this paper. It's a joint work with Fernando Marshall, also from São Carlos. So, let me finally give you the precise definition of a rotational submanifold in this context. This is just an adaptation of the classical construction given in Marcos and Manfredo's paper. We start with either Euclidean space or Lorentzian space and look at the standard models of the sphere or hyperbolic space inside it. Then we take a subspace of that flat space with this dimension, and we just realize that if we intersect it with this cylinder, we get a totally geodesic cylinder inside it. And now, if you consider the group of isometries of the flat ambient space that fix pointwise the subspace, and we take a curve in a cylinder sitting in the subspace that lies in one of the two half spaces of it, determined by a further hyperplane contained in that, we obtain, and we let that group of isometries act on the curve, we generate this rotational submanifold, and the curve alpha is called the profile curve of it. So this is just the standard construction of Marcos and Manfredo. Just in their case, they always take this subspace three-dimensional and take either sphere or a hyperbolic space here instead of the product space. Well, it turns out that rotational submanifolds are also always in class A. And in fact, they can be characterized among submanifolds in class A by this corollary. They are just the submanifolds in class A which are given in terms of that general construction I showed you by starting with as an umbilical submanifold of the base space. Well, a geodesic circle in the case of 2 dimensions. And they are characterized by this structure of the second fundamental form. In the hypersurface case, it just says that we should have only 2 principal curvatures, one of them with multiplicity 1, having the vector field T as a principal direction. Remember, T is the tangent component of the unit vector field spanning the vector R. So, with this corollary, we immediately see that umbilical submanifolds are rotational ones because, of course, their second fundamental form have in particular this structure. So they are rotational submanifolds. And we now just have to add the umbilicity condition. But this would not certainly enable us to get a classification unless we first were able to show that they reduce codimension. Otherwise, the profile curve would be a curve in a totally geodesic submanifold of very high dimension. So what we have done is just extended the usual criterion for reducing codimension of isometric emergence in space forms to the case of those products. And the result is very similar to the one you all know. In the case of space form, of course, the usual condition for a submanifold to reduce codimension is that this first normal bundle, which is the subbundle of the normal bundle spanned by the image of the second fundamental form, be a parallel vector subbundle of the normal bundle. In this case, we just have to add this vector field eta, which is the normal component of the unit vector field spanning the vector R. So except for that, the result is pretty much the same. And from this result, well, the problem is now, like in the case of space forms, to obtain some geometric conditions for this to happen. In the case of space forms, this has been done by Marcus in his very well-known result. And we just had to adapt his proof to get this theorem. So, in order for this vector subbundle to be satisfy the condition in the previous result, which allows you to reduce codimension, this is equivalent to those 2 conditions being satisfied. They are the same as in the case of space forms, just replacing the vector subbundle L by the first normal bundle. So, one application we were able to get from this result was a simpler proof of a recent result by Manfredo, Hilario, and Renato, who studied surfaces with parallel mean curvature vector in those product spaces. It's easy to see that, well, of course, in this case, the second condition is trivially satisfied. And if such a surface doesn't have flat normal boundary, it's easy to see that it has to lie in a slice of the product space. And then we can use a well-known result by Yao to say how they are all. And if they have flat normal boundary, this condition is trivially satisfied also. And then we conclude that the submanifold can be reduced to 3 at most. 2 is the dimension of the first normal bundle, and then 1. You add one more dimension if this vector field does not lie in the first normal bundle. Okay, but back to the case of umbilical submanifolds. Now we know both that this submanifold is umbilical, is rotational, and that the codimension is at most 2. So we just have to compute the profile curve, which is a curve in S2 cross R, or could be in S1 cross R. So this gives us a system of ODEs for the 4 coordinate functions. But fortunately, the system is decoupled. I mean, if we choose the first coordinate to be S, I suppose it to be a graph, then this immediately yields the last coordinate functions, and we are reduced to looking for the 2 remaining ones, which turn out to be solutions of the second order system of ODEs, subject to this further restriction, which is just the condition for the curve to lie in S2 cross R. But it turns out that we can solve it completely. This is the solution. And with that in hand, we are able to show that all such submanifolds are parametrized by that map YPQ I showed you at the beginning. So this leads us to the best part of the talk, which is the end.